All right, Red Nation. Today we're going to be talking about photon counting CT detectors. They're going to have to count pretty high though. We're often talking about 10 to the ninth counts per detector cell per readout on our CT detectors. Again, that's what makes CT so much more challenging than a modality like PET, where they've been using photon counting detectors for some time. I'll quickly go through scintillation-based detectors. If you haven't seen our video on CT detectors, check that one out where we go through in a little bit more detail on the scintillation-based detector. But the idea of the scintillation-based detector, which is the gold standard in the field today, is that the X-rays come in, the X-ray is then converted from an X-ray into light photons. So we're talking about hundreds of light photons per X-ray photon. Then those light photons are measured, they're converted from the light into an electrical signal by what's called a photodiode. And there's a little bit of an optical reflector surrounding each of the scintillator crystals so that the light stays inside of each of those little local areas and then gets read out by the photodiode. So if you think about your photons as they're coming in, what actually is going to happen, we're going to show plots like this later where we want to measure individual photons and what the peak of an individual photon would be. But on these type of systems, we actually don't have the ability to do that. All of the X-ray photons that come in are actually converted to light photons, and then that is all converted to the electrical signal. So what we say is we call that an energy integrating detector. And ASIC is called an application specific integrated circuit. That's the thing that's actually doing that conversion. So we'd say we have an energy integrating ASIC. So the ASIC is going to convert from our electrical signal into our digital signal. So a very frequent terminology that you're going to hear now is EID, or energy integrating detector. That's in comparison with a photon counting detector, where you're going to have some ability to actually distinguish individual counts of the X-rays. So some limitations of our scintillation-based detectors is that number one, like we talked about, they are energy integrating. The X-rays are converted to photons, and then that's read out, and there's no way to actually give the different energies different weights. So the higher energy X-rays are actually going to get more weights because higher energy X-rays are going to generate more visible photons, and thus they're going to get a higher weighting when you add them up. It's not that we're adding up in a computer, they're being added up as all the light gets generated within that. Also, no inherent spectral capabilities with our standard detectors, so we have to add something to the system. We either have to add the ability to switch the KVP very quickly, or we have to add two tubes and two detectors to a system, or we have to add another layer of scintillator behind our initial scintillator. These are the type of things we can do to get spectral imaging, or what's called dual energy information, in our CT. That's not built in with a standard scintillation-based detector. Also, the difficulty in making extremely high resolution imaging with our standard scintillation detector, because we have some region where we need to have optical separation between each of the little scintillator blocks. As we make our detector elements smaller and smaller, that region of optical separation is actually going to become a bigger fraction. So your detector is going to get less efficient if you make it smaller and smaller. Any circuit in general is going to have some electronic noise associated with it. And with a standard energy integrating detector, we don't have any way to reject the signal that has to do with the electronic noise. The idea here is we'd like a way in very low signal environments to be able to actually suppress the electronic noise. Photon counting detectors have some promise to actually improve in each of these areas. And traditional photon counting detectors are made of cadmium telluride or cadmium zinc telluride. And the idea here is this is a solid state material. The X-rays are going to come down and interact with this material. There's a relatively high voltage on the order of 1,000 volts applied from the bottom to the top of this material. The material is relatively thin, as are today's scintillation-based detectors. And as the X-rays come down, they're going to interact and they're going to generate what we call electron-hole pairs. Electrons are going to get pulled toward the anode, and the positively charged ions are going to get pulled toward the cathode. You're going to have negative electrons getting measured at the anode. The anode is separated into little small rectangles, and right now we're just looking into the board. So you're kind of looking at a cross section through there, and at one cross section through there, you can see this is a little small area of the anode. And the idea is that those electrical charges are going to get measured on the anode. And now our pixelation on the detector actually doesn't rely on having separate individual elements, but it relies on the ability to read out these discrete anodes separately. Your electrical signal comes down in there. And then the idea is that if you look at the electrical signal, which is coming out over time, as the X-rays interact, we're going to get peaks here, which have higher energy associated with the energy that's being deposited from those X-rays. We then have the ability to what's called bin our measurements into different energy bins. So below a certain level, we will say this is just our noise threshold. And anything below that level, we will assume is just noise, because very low energy X-rays actually won't penetrate through the body. So it's a relatively good assumption to have a level below which you say, this is just noise. And then the idea is that you can now have two different energy bins, for instance. You could have a lower energy bin and a higher energy bin. And that's going to go into what we call a photon counting ASIC. So it's a little bit different circuitry in our application specific integrated circuit, and it's going to be counting X-ray photons. Now that we know the schematic, we can talk about some of the challenges that we encounter when using photon counting in reality. The first one is going to be called pulse pileup. So what happens if one X-ray comes in and then very quickly, before the signal can get read out, another X-ray comes in? That's what we call pulse pileup. And there's no way to distinguish when that happens. So if they happen essentially right on top of one another with a very small delay, then you see the combined signal is actually one peak and it has a higher energy. So what's going to happen in that case is you actually now think that a higher energy X-ray came in instead of these two lower energy X-rays. There's also some scenarios of pulse pileup where there's just a little bit of a delay, but there can still be problematic in terms of assigning the energy for that X-ray photon. So if there's just a little bit of a delay, you could get a combined signal, which is actually goes up, and then has one peak, and then another peak, and then goes down. And in this case, you can tell now that there's two photons. You could still detect that there's two photons by the separate peaks there, but you're going to have difficulty assigning the individual energies for those photons. So this is another scenario where the pulse pileup is going to lead to a degradation in our image signal. For photon counting detectors, we talk about different regimes. The ideal regime is what we call linear. So in that case, there's going to be a direct relationship between the pulse height and the detector signal. So essentially the KEV of our X-ray, if that comes in, we would get a detector signal which would read out and would be directly related to the energy of our X-ray. In reality, what can happen is we can have a degradation for our higher energies. And this is what we call the non-parallelizable region, because you can see it's not a straight line, but it actually never goes down upon itself. So we always know, because this is what's called monotonic, we always know that we can have a mapping from this signal to this linear signal. But there is some actual energy resolution which is being lost by these non-ideal events in photon counting. If you're in what's called the parallelized regime, there's actually going to be ambiguity for photons down here in the parallelizable section. This is the case where there's a significant dead time where the detector is not actually able to read out the X-rays. So you definitely don't want to have a system which is operating down here in this paralyzed state. This technical issue we want to talk about is charge sharing. So the idea here is, again, we'll draw the X-ray coming in, and the X-ray is going to make electron and hole pairs, right? The electrons are going to flow down towards the anode, but let's say the X-ray actually interacted right in between the middle of two anodes. So if that's the case, that the X-ray is going right in the middle of two anodes, then the charge is actually going to be distributed between the two. So this charge sharing, I think, should be better called charge splitting, because the charge is actually split between the different anodes. And the idea here is that you have an ideal signal, which would be measured here from your X-ray, but in actuality, you're going to get multiple signals. And I'm just showing two here for these two neighbors, but you can think of even four neighbors in the 2 dimensions. So this is the case where the signals split equally if it landed right in between the two. But in reality, there can be any numbers of splitting. If it lands a little bit closer to one than another, then one of the signals might be higher and the other might be lower. So this charge sharing is actually going to be problematic in terms of degrading our image fidelity. We also have what's called K-escape fluorescence. So our X-ray comes in. If you haven't seen our video on photoelectric effect in Compton, check that one out. In the photoelectric effect, the idea is that an inner shell electron gets kicked out, and then there's a vacancy there. And an electron from the shell above it is going to drop down. And in order to preserve energy, it's actually going to emit what's called a fluorescent photon. So in that scenario, that can actually happen inside the detector material. So you have actually a fluorescence event, which will then generate electron hole pairs itself. And it will do that just a little bit away from the primary interaction site. So in this scenario, you can think of an ideal pulse height, and now you're actually splitting up that pulse into a primary one and another one, which is the energy of that fluorescence event. On top of this, you can think about the fact that both the primary and the fluorescence event also potentially can have charge sharing. So you'll have both the K-escape and charge sharing happening on top of one another. If you have all these things added together, how does that change what your detector signal looks like? So the ideal scenario would be if you had like this perfect detector where it came in, if you gave it just one X-ray photon of one given energy, and you would get this nice signal like this. But imagine we could give the detector many photons of one given energy, and we would like to see a nice sharp peak like this. What you get rather in reality is something that looks like this, where you'd like to have one sharp peak, but what you get is an actual peak, and then you'll get a smaller peak, which is at a lower energy, which is the energy of your actual X-ray minus the energy of the fluorescence effect. It's your fluorescence difference peak. You'll also get a fluorescence peak, so this is the energy of the fluorescence effect. You'll get a general large number of measurements here that are associated with charge sharing at the lower energies. So these non-idealities lead to actually degradation in your energy separation on your system. In designing a system, you actually have a finite size of pixels that you're going to use in order to read out that detector. And you could have either very small pixels or a little bit larger pixels. And if we talk about these different effects, they actually have different ideal scenarios. The charge sharing, you'd actually like to have a relatively larger pixel, right? Because as your pixel gets smaller and smaller, then you're going to have more and more area on the border that's actually leading to shared charge. So in terms of charge sharing, you'd like to have a little bit larger detector. In terms of pulse pileup, however, you'd like to have the smaller detector, because if your detector is smaller, there's going to be less of a probability at any one time that there's X-rays that are interacting in there. It's creating what's called a dead time, wherein the readout cannot be effectively occurring. Also means that if you would like to look at just high spatial resolution, what you'd like is relatively small detector pixels. If you'd like to look at good spectral resolution, what you'd like is relatively large detector pixels. These are trade-offs you have to work on these type of systems when you're doing the detector design. We're going to switch real quickly here to talk about a different type of sensor that's been used actually for a long time in high energy and nuclear experiments, and it's actually silicon. So the idea here in this type of experiment would be that you'd have charged particles for nuclear physics experiments. So I worked on this one back around 2000 when I was undergrad at the National Superconducting Cyclotron Laboratory. These were not unique though. There's a number of these throughout the world at the time and have been even improved on since. But the idea is that you would have nuclear charged particles coming in here and that they would be measured in the different silicon arrays, and you would have one set of strips going one direction, another set of strips going the other direction, and they would go through, they would just deposit a little bit of their energy along each of these layers, but then you could tell essentially on the grid where they were passing through there. And then you would have another material here, which is a scintillation material, more like the traditional detectors in CT, and they would have all of your energy of your charged particles deposited there. Silicon actually has a lower cross section for interactions with our medical x-rays. So if you have a detector like this, actually most of the energy would pass straight on through and wouldn't be deposited in your detector. Danielson had the idea, what if you take one of those silicon-based detectors and instead of using it like they normally do in a high energy experiment, let's turn it on its side so that actually most of the energy will be able to be deposited because now we'll have a long path length of silicon. So this is another possible way that you can do photon counting in CT. And in this type of scenario, the X-rays coming through and the X-ray can deposit its energy throughout the different depths in the silicon. In that manner, you can allow for significantly higher count rates without getting in the region of significant pulse pileup. If we look at the silicon detectors and talk about some properties of them, like we said, the detector, actually the material has to be at least 10 times thicker. So it's what we call a deep silicon detector. Interaction probability isn't as high in any one region. You actually need a much thicker detector. Also, the possibility of Compton scatter in silicon to a higher degree than in traditional detectors. And this is similar to the K escape that you have in your cadmium telluride, wherein you're going to get crosstalk with neighboring channels. Now, primary advantage, like we talked about, is these different depth segments allow us to have higher count rates, and also the mobility of your charges within the silicon itself allow for very fast readouts on these silicon detectors. And at a high level, what we want to talk about is the promise of these photon counting detectors, whether they're cadmium telluride or silicon. They offer significant promise in terms of overcoming some of the limitations that we have on the scintillation-based techniques. If the desire is to generate just an image using all the photons, you can weight the photons more appropriately, wherein you could give them an equal weighting so that all the photons, after you count them, you're going to count them all equally. And that's different than our energy integrating detector, wherein the high energy X-rays actually got measured with a bigger weight because they were making more actual visible photons that were getting measured. And we actually like the contrast a little bit better at lower energies, especially for bone and iodine imaging. You also have inherent spectral information. So you don't have to change the KVP. You don't have to have two tubes and two detectors on the system in order to get dual energy imaging. So the higher spatial resolution. So both of these approaches, the cadmium telluride, now you're actually not making actually smaller pixels physically out of the material in terms of dicing the material. You're actually just changing the readout on the anode. So that allows you to actually make significantly smaller pixels. And in the case of silicon, you can also make significantly smaller pixels with this edge-on detector design. Photon counting in general allows you to have the different bins like we talked about, and allows you to set an energy threshold below a given threshold that we are going to say is the minimum threshold. That can actually just suppress the electronic noise so it doesn't contribute to our image signal at all. So these are the promises of photon counting CT. Watch from the vendors to see what comes out over the next several years and see how photon counting CT actually starts to play a role more and more in terms of clinical imaging in CT. If you haven't seen our video on CT detectors, definitely check that one out now, because the bread and butter of CT imaging is actually performed with scintillation detectors. You want to make sure you really understand those well.